Quebec Bridge, a testament to engineering ambition and resilience, a historic challenge in the early 20th century, the need for extensive infrastructure to support rapid industrial growth became evident across North America. The Quebec Bridge, spanning the St. Lawrence River, was poised to become a crucial link between the Canadian provinces of Quebec and Ontario. The objective was clear: to build a bridge that would facilitate the burgeoning railway system while accommodating future highway traffic. Yet this monumental task would face challenges that would test engineering principles from span length to stability. Setting the scene, time and place: the St. Lawrence River is both a natural barrier and an opportunity, compelling engineers to bridge its expanse for commerce and connection. The Canadian government, recognizing the importance of a robust transportation network, chose the site for the Quebec Bridge in 1897. The envisioned nearly mile-long steel cantilever bridge would eventually become the longest in the world. This landscape was not only defined by the river, but also by the complexities of constructing such a monumental structure, driven by the need for modern rail transport. Quebec City was on the brink of transformation, with the bridge seen as a catalyst for this change. The engineering challenge: designing a bridge of this scale presented multifaceted engineering hurdles, primarily achieving the necessary span and ensuring stability against environmental forces. While engineers at the time had a growing understanding of materials, they lacked experience on the scale proposed for the Quebec Bridge. Initially, the design was entrusted to Gustave Eiffel, known for the Eiffel Tower. However, commercial constraints led to his dismissal, and the project was taken over by Canadian engineer James Bowser and his team. Their challenge was to design a bridge that could handle dynamic loads from trains, wind, and ice, while also withstanding catastrophic events like flooding and seismic activity. Conceptual development: the solution: the engineers chose a cantilever design, allowing construction without falsework, temporary supports needed until completion. This design effectively distributed weight and managed stresses. The initial design called for a main span of 1,800 feet, 550 meters. Bowser aimed to push limits, requiring extensive calculations to ensure the bridge could support trains and withstand environmental conditions. Steel was selected for its strength and lightweight properties. However, the quality and availability of steel posed challenges. Systematic testing was required for material reliability. Stability required robust cantilever arms to manage bending and shear forces. The bridge needed a resistance system to handle wind loads, crucial due to the river's exposure and temperature variations affecting metal properties. Using methods predating modern modeling, the team relied on manual calculations and physical models to test their theories. Key systems and mechanisms: construction began in 1900, incorporating several innovative systems. The main structure featured a truss designed to effectively distribute loads while enhancing strength without significant weight. Cantilevered piers, built of robust masonry, anchored the cantilevers while accommodating thermal expansion and contraction. The upper deck utilized a lattice structure, enhancing load-bearing capabilities while maintaining aesthetics. However, challenges arose during construction. A catastrophic collapse on August 29, 1907, just days before finishing one cantilever section, took the lives of 75 workers, sending shockwaves through the engineering community. Difficulties and breakthroughs: post-disaster investigations revealed critical flaws in the engineering approaches. This incident underscored a need for a comprehensive understanding of both static and dynamic forces. The project management was revamped, and design efforts resumed with a renewed focus on safety. Design modifications included additional bracing and recalibrated load distributions. A rigorous quality control approach emphasized the reliability of steel components. The setbacks spurred innovation in construction techniques and led to a new paradigm of safety and accountability in the industry. Completion and legacy: on April 21, 1917, the Quebec Bridge was completed, measuring 3,233 feet, 985 meters in length, eclipsing all predecessors. The cantilever design set new standards for future bridge construction globally. With 2 roadway levels for vehicular and train traffic, the bridge catered to transportation needs and highlighted a commitment to connectivity. Its elegant steel filigree transformed the landscape, contrasting beautifully with the riverbanks. Over the decades, the Quebec Bridge has proven resilient against heavy traffic, severe weather, and seismic forces. Ongoing maintenance has ensured its continued functionality as a cornerstone of Canadian infrastructure. Real-world impact and significance: the influence of the Quebec Bridge extends beyond its physical form. Its design lessons impacted engineering principles worldwide, illuminating the relationship between design rigor and material properties. It serves as a cautionary tale about the importance of safety, shaping legislation and protocols governing structural integrity today. The narrative of the Quebec Bridge is one of human endeavor, celebrating innovation while acknowledging the nature of failure. It remains a vital reminder of the complexities in engineering undertaken to realize ambitious visions. In conclusion, the journey of the Quebec Bridge embodies the trials, tribulations, and triumphs of engineering. It signifies a reliable connection across both physical and historical divides. Today, as it continues to function, it reminds us of resilience, adaptive design, and the pursuit of progress in adversity, guiding future generations of engineers in their relentless innovation quest.